My name is Jim Hutchins, and I'm a teacher in the Health Sciences Department at Weber State University. We're in the Biomedical Core class, and this is Module 2, which is the atomic level of organization. I'm going to break this presentation up into several smaller presentations rather than do the whole module at once. And so you'll have 10 or 15-minute videos that'll cover several different objectives. This first video in the series for Module 2 is going to be over objectives 1 through 5, and we can group those as properties of matter. So if you go to your study guide, you'll see that this is the first slide in the study guide that introduces you, or it's a title slide for the module. We're going to start off with several definitions, and so we're going to define elements, atoms, molecules, and compounds. An element is a substance that can't be split into simpler substances by chemical means, and what we mean by that is that it's a substance that if we take it apart, if we use any kind of chemical means to take a compound like water apart, and we'll learn what a compound is later, but if we take a compound like water apart, once we get down to the hydrogen atoms and the oxygen atoms in water, then that's as far as we can go with it. And beyond that, we can't split things into things smaller than hydrogen or things smaller than oxygen, and so we call those elements. The things that make up elements are atoms. Those are the smallest unit of matter that retain these properties and characteristics of the element. So if we have a small unit of matter that acts like hydrogen, then that's a hydrogen atom. If we have a small unit of matter that acts like oxygen, then that's an oxygen atom. This lists the main chemical elements of the body. What you'll see when we get to the periodic table is that this corresponds to the elements that have colored blocks in the periodic table, the ones that we're calling major or minor or trace elements in the human body. And so we need to know each one of the chemical elements that's listed here. We need to know both its name, its relative prevalence, and we need to know also what the symbol is for that atom. As we'll see when we do the periodic table, in most cases the symbols are easily derived from the name of the element. In a few cases they're not, because we use old Latin names. We'll talk about that when we get to those objectives where we're looking at the periodic table. The main chemical elements in the body are oxygen, carbon, hydrogen, and nitrogen. So you already know that, for example, the body is made up of a lot of water. We'll get to the specific amount of water later on in the course, but a majority of the body is water by either weight or number of atoms, and water molecules, we'll learn later on in this module, are made up of 2 hydrogen atoms plus an oxygen atom. And so that water, the constituents of water, are included in the major elements. All life forms on Earth are based on carbon. We'll see why in the next module as we talk about how carbon has a lot of diversity and how it can combine with other things. And so since we're carbon-based life, carbon is a major element in living creatures such as human beings. And we'll also see in Module 3 that nitrogen is a component of what are called proteins and nucleic acids. So nitrogen is classified as a major element in the human body. The more important these elements are, the more likely they are to come up over and over again in the course. The more likely they are to come up over and over again in the course, then the more likely we are to ask you exam questions about it. That's just a little pro tip there. The lesser chemical elements of the body include calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iron. I'm not going to burden you with reading all of the material that's on these slides. I'm going to leave that for you to do on your own. This is the table from the book, table 2.1. So the main chemical elements of the body, showing you a percentage of the total body mass. Not a number that you need to memorize, but just so you know where they are by weight and by occurrence in the human body, so that you know, for example, that oxygen is the most common element by weight. Hydrogen would be the most common element by number of atoms. We'll get into that distinction a little later on. So continuing with our definitions, we have elements, atoms, molecules, and compounds. A molecule is two or more atoms that share electrons or trade electrons and thus form a chemical bond. A chemical bond is something we're going to talk about a little bit later in this module. So they can be two atoms of the same element. For example, O2 is symbolizing two atoms of oxygen that combine together to form an oxygen molecule. So an oxygen atom bound to another oxygen atom is called an oxygen molecule, and we symbolize that with O2 because there are two oxygen atoms in this. And we have two hydrogen atoms combined with an oxygen atom, then those are atoms of different elements, still a molecule. We call this molecule H2O because there's two hydrogens for every oxygen. We'll talk about the special properties of water a little bit later on in the module. A compound, on the other hand, is a molecule because it contains two or more atoms, but in this case the atoms are different elements. So water is not only a molecule, H2O is not only a molecule, but it's also a compound because it has both hydrogen atoms and oxygen atoms. Sodium chloride is a molecule and a compound because it has sodium atoms and chloride atoms. Calcium chloride is a molecule and a compound because it has both calcium atoms and chlorine atoms. Oxygen is a molecule, but it's not a compound because it has two oxygen atoms. And as is noted here, the small or subscript number indicates the number of each atom in the compound. We see in the image, we're not going to worry about the breakdown of the nucleus very much. We're certainly not going to look at quarks, but we can get some idea of the size that we're operating at with the metric prefixes that we've used previously. So a molecule, as it shows here, tends to be about 1 nanometer or 10 to the minus 9th meters or 1 billionth of a meter or 1 millionth of a millimeter in diameter. And an atom is about 1/10 the size of a molecule, as is shown here. So an atom, for example, a hydrogen atom, tends to be about 1/10 the size of a typical molecule, just to give you an idea of scale. So that's another way of putting this is to say that we could have 10 million atoms lined up along a ruler, and together, laid end to end, they would make up 1 millimeter. So the next thing we're going to talk about are the physical properties of solids, liquids, and gases. A solid has a definite shape and a definite volume. And we're about to look at an animation that's going to show us why this is. This has to do with the way that the atoms are arranged inside of a solid versus a liquid versus a gas. And we'll look at that arrangement in an animation in just a minute. A liquid has an indefinite shape. In other words, it takes on the shape of whatever container we put it into. So if we pour milk into a jug, the milk takes on the shape of that jug. That's a characteristic of a liquid. But it has a definite volume. It doesn't change the volume of the milk to pour it from a jug into a pitcher, but it does change the shape of it. And a gas, on the other hand, has an indefinite shape and an indefinite volume. So not only does it take on the shape of the container, but it can change its volume depending on the temperature. And that's because the particles, as it says here, are independent of each other and relatively far apart. Now we have an animation which is going to show you the different states of matter by looking at the atoms in that state of matter. If you want to play with this animation yourself, it's in demonstrations.wolfram.com/thermal motion in a solid. That's printed in your study guide if you want to go to that. And there's another one that I'm going to use called molecular motion in solids, liquids, and gases. And so we're going to be looking at that now. These are a series of animations from the program Mathematica that are showing molecular motion in solids, liquids, and gases as the title is demonstrating. In the first few frames, we're looking at molecular motion in a solid, and you can see that in the solid state, the atoms, which are represented by the balls or the spheres that are moving around inside this box, are constrained and they're tied to one another in what's called a crystal lattice. Each of the atoms is in a precise relationship with the other atoms, and they're able to move a little bit, but not an awful lot. Now, if we change the state to a liquid state, then what we're going to do is just click on this and bring the state up to a liquid state, and we'll see things changing in this material. And now the atoms are in a different kind of relationship with one another. Notice that they're not in a rigid array, they're not in a mathematically precise arrangement, but they're all at different angles to each other, and there's a lot more room for movement, which is what it gives a liquid its special properties. The solid that we saw before had a defined volume and a defined shape. The liquid has a defined volume, but it doesn't have a defined shape. It can change shape, and that's because these atoms that we see here can slide past one another. We're going to go ahead and increase the temperature by clicking on this plus here, and we're going to go through one more transition now from a liquid to a gas. And we can see that as the liquid starts to boil and goes into the gaseous state, it's going to make that transition between 400 and 500 degrees Kelvin. And now in the gaseous state, there's no defined volume, there's no defined relationship between the atoms. The atoms are just free to bounce off of one another, and this is characteristic of a gaseous state, as we see here.